Hey, John here. Let's talk about things called interrupts and traps. Now, these are going to widely vary depending on the kind of CPU that you're using, or even different variations of the same CPU. Every vendor does this very differently. So in the simplest of terms, let's define this and then have a look-see at one or two examples. Simplest of terms, an interruption, or a trap, sometimes called an exception, again, depending on the vendor that you're using. They all have different terminology. It is a disruption in the flow of the CPU's normal execution of a sequence of instructions. It is exactly what the word means. It is an interruption to the CPU and what it would normally be doing. We have two types. There's synchronous and there's asynchronous. Asynchronous, we tend to call these interrupt requests because they are literally requests usually by a piece of hardware for service. Synchronous interrupts are usually referred to as traps or exceptions by, the various vendors, okay? So a synchronous, and you got to be careful how you say that, those that are synchronous tend to be an instruction that would fail as a result of an error of some kind. For example, let's say you're going to access an invalid memory location, in a load instruction or something like that. Or you're going to use a register number that's invalid in a register like on the RISC-V, the CSRS instruction. You could just say, hey, I want to read some register number, F015 or something like that, which is not even valid, okay? And that wouldn't even assemble, by the way. But you know what I mean. If you give it an invalid number that it doesn't want to let you use, that would be an example of an exception, an exceptional situation that would trap out of the current sequence of instructions, okay? These are called synchronous, by the way, because they're caused by the execution of an instruction. These are called asynchronous because they're caused by something other than the CPU executing instructions. They're usually caused by a device that signals that it wants some sort of service. Okay, maybe a disk that you've asked, move the head to some track on a rotating platter, right? Well, it takes time to do that. So the CPU, if you write your programs appropriately, can go off and run other code while the disk drive spins the head, waits for the disk to rotate around or move the head out to where it's supposed to be and that sort of thing. And an interrupt would then be created by the hard drive to let the CPU know that it's ready for the next command that it's supposed to do, like reading or writing one of the sectors perhaps on the track that the head was moved to. All right? Asynchronous almost always are called interrupt requests, and I mean that by most vendors refer to those as interrupt requests because they come from external hardware. Synchronous are usually called exceptions or traps, and they're caused by, and they occur in synchrony with a specific instruction that fails for some reason. All right, so let's look at a couple of examples. Synchronous trap might be this. This is a real easy way to cause one, right? Char star p equals null pointer, and then say star p equals something. I'm trying to write something into memory at a address that is a null, which is 0, okay? That's going to give you what we would normally call a null pointer exception, okay? That would cause the CPU to stop running your program. How do you think it stops, right? It gets an exception or a trap. We'll look more at what that is from the perspective of the CPU in a second, okay? Asynchronous interrupt requests, like I said before, could come from something like a counter or sometimes a timer that overflows, right? Maybe you've got a counter that's just counting a clock pulse and it's counting up. And when it gets to all binary ones and flips back to 0, that overflow, the carry out of the most significant bit, might be used to generate an interrupt request. Or maybe you have a UART out there that's receiving bits serially or transmitting them serially. That takes time. So the CPU might be running a piece of code, and while data is arriving on a serial port like a UART, and when the data has completed arriving, it could generate an interrupt to let the CPU know, and that would be a really good time to look at the UART and collect the data that is just received. So how then does that work? So let's say this is a machine that we've got, right? We got a CPU, we've got some memory, and they're hooked up to some decoders, and we've got a counter over here that's also connected up to this data bus down here. When this counter reaches its maximum limit, it'll eventually generate a carry that comes out of it, right? From the most significant bit. It would flip back to 0, carry would become true, or it would be overflow. These really kind of mean the same thing in this context, okay? Means that, I added 1 to something and it can't hold it anymore. Therefore, there's been an overflow situation, or you say a carry out of the most significant bit. Well, you can hook this up into your CPU. Quite often, there's a special signal down here called interrupt request. And by doing so, every time an overflow or a carry would come out of your counter, it would assert this interrupt request signal back to the CPU, which could then react and invoke some code to deal with the fact that this situation has occurred. So how then does the CPU react to its receipt of an interrupt? Okay, well, it depends if it's synchronous or asynchronous. Obviously, if it's synchronous, we have to stop the execution of the instruction that has failed. We have to abort that. Okay? Obviously, if you're reading from an illegal memory address, you don't finish it and then stop. You have to stop it right in the middle of that instruction. If you have an asynchronous interruption, what happens is that the current instruction will be completed in its entirety, as it normally would. Regardless of why the CPU has become interrupted, what does it do? It's going to save a copy of the program counter somewhere. And the reason it needs to do that is so that if you want to, your code can go back to what was interrupted. Okay? Almost always, if you get an interruption from a disk drive or, some sort of a device, a timer or something, you're going to go back and pick up where you left off. If you have an illegal instruction, it depends. Maybe you want to try it again, or you're going to just stop that entire program. If you're an operating system and somebody accessed an illegal memory address, generally you'd stop the program. And my point is you wouldn't go back and resume it. However, no matter what, you do want to save it right away in case you want to go back and resume your code. Okay? The second thing that happens, and here's why you have to save the program counter, is that the CPU will load the program counter with a special address to begin executing some code to address the needs of this trap or interrupt request that has taken place. Now, this varies widely on your manufacturer and stuff like that. Different type of CPU brands, whatever features you even have enabled on your CPU. You might have to save something related to like security modes, what mode the machine is in, and things like that. If your CPU has, supervisor privileges and user privileges, like some instructions are not allowed to be used by certain programs and some other instructions are allowed in different programs and stuff like that, the CPUs that provide features that govern those sorts of things usually have some sort of mode settings, and you want to remember what those are so you can restore them again, just like the program counter up here. Okay, what about your memory management unit? Well, if the program that was interrupted is using virtual memory, you may or may not want to handle the interrupt or exception using the virtual memory translations that are associated with whatever process was disrupted. Okay, you might need to save those and then restore them later in order to restart the program later on. There could be other things that change too that you need to save, like for example the ALU flags if your CPU has those. I mean, obviously, if you have an interrupt from a device of some kind and the handling of that interrupt adjusts things like those ALU flags, right? You need to put them back the way they were in order to resume whatever program was disrupted, okay? After you've saved the state, all right, let's just say here you just save the heart or the CPU, depending on your vendor. All right, you want to save it in such a way that you can restore it if you want, okay? Once you're done saving the state of the machine, the CPU has done its job to deal with that interrupt request. It is essentially done. However, the software that is the so-called interrupt or the trap handler now takes over, okay? In order for that to happen, the CPU just starts, resuming the execution of code at this new address. So what does it really then boil down to? It effectively makes the CPU call a subroutine at any arbitrary place, in time while a program might be running, okay? And that special subroutine exists for no other purpose than to react to and to provide service if an interrupt should occur or a trap or an exception takes place while processing an instruction that may be illegal. So let's look at a part of a very old manual. It looks like it's been scanned in off a fax, for crying out loud, of the 6502. All right, these things were created originally by, I think, a company called MOSTech. You can read all about that here in Wikipedia. Now, these processors were used in machines like the Apple II or the NES gaming system or the Atari 2600 and a lot of the Commodore computers like the VIC-20 or the Commodore 64 and things like that, okay? So these are fairly well-known CPUs. Let's look and see how these things work, all right? So here's the manual here, and on page 7, I believe, if we go back to page 7 here, it talks about various things. Oh, here's the overflow flag and when that happens and stuff like that. Down here, there's a paragraph on how interrupt requests work. All right, let me zoom in here and scroll it over. What happens when this signal here, there's an IRQ signal, just like I drew in the diagram a minute ago. Theirs has a bar over it, which means it goes low in order to assert the situation to be true, okay? And, what does it do? Here's the entire documentation for how an interrupt request works on a 6502. Super simple, all right? What does it do? All right, it says it'll complete the current instruction that's being executed, right, before it recognizes the request. At that time, the interrupt mask and the status code register will be examined, all right? These CPUs, usually that have interrupt requests, have a way, register or something inside of them that allow the programmer to say, do not allow interrupts to occur, just ignore them for a little while. You can then re-enable them later. It's part of what you might do around certain kinds of critical code sections, all right? It's sort of like creating a lock so that other processes or threads don't get in your way. Well, sometimes you need to disable temporarily the receipt of an interrupt request signal, okay? So what does it say down here? If the interrupt mask flag is not set, then the microprocessor will begin the interrupt sequence. In other words, if it is allowed to occur and hasn't been masked off, it will then do what? The program counter and processor status register, okay? Those are the only two things that hold the state beyond the regular user registers in a 6502 processor, okay? The processor status register is where the flags are for the ALU, okay? Those are stored on the stack. They're just pushed onto the stack. The microprocessor will then set the interrupt mask flag high so that no further interrupts may occur. Now, that's kind of important if you think about it. If you have a lot of interrupt requests in a row that all cause stuff to be pushed onto the stack, and you don't have any way of controlling that, you could overflow your stack, all right? So on the 6502, as soon as the processor recognizes that an interrupt request has occurred and reacts to it, it will disable subsequent interrupt requests from occurring. It's up to you as a programmer to decide when to set this flag back to low again to let them resume. Okay, and there's a whole strategy about when to do it, why to do it, how to do it. It totally depends on how your operating system or user programs or freestanding programs were designed to operate. You get to choose, okay? So anyway, what does it do? It pushes the program counter process status information out of the stack. It disables any future interrupt requests from being recognized. And at the end of this cycle, it says the program counter will low will be read from here, and the program counter high will be read from there. And what they're referring to there is in these days, okay, these were 8-bit CPUs, and they had 16-bit addresses. So in order to say that the program counter was loaded from address X, what they do is they specifically state that the least significant byte of the program counter will be set to the value stored in this address in the memory. The most significant byte in the program counter will be set to whatever value is in that address of memory. And these are the highest 2 bytes in the entire memory of the machine because it only had 64K, which is 4 hex digits worth of, numbers, okay? So FFE, FFFF are the last 2 bytes, and you just simply put a number in there that says this is the address to go to if an interrupt ever occurs, okay? At which point, the CPU resumes execution. Now it talks about 3K resistors and things like that. This is more the electrical engineering side of things that don't concern us right now, okay? So what does a 6502 do if it gets an interrupt? It just simply sets the program, it saves the state of the machine into the stack, wherever the stack pointer currently is pointing, and then it loads the program counter with the an address that stores at FFFE and FFFF, and it's done. Things were much easier in 1975. Now, if we move down to page 8 in the 6502 manual, we'll see that there's an instruction called CLI over here, which stands for Clear Interrupt Disable Bit, okay? And the opposite of that is SEI, for Set Interrupt Disable Status, I guess. You would think that they would have come up with a symmetric naming scheme for these 2 instructions, but there they are in all their glory, okay? So SEI means set the mask. In other words, don't allow interrupts. CLI means allow interrupts to take place from here forward. We've also got some special instructions here called return from interrupt, which is different than return from subroutine. Now, why do you suppose return from interrupt would be any different than returning from a subroutine? After all, I told you that the point of the CPU is to save the CPU status so that it can call a subroutine. Well, it turns out that part of returning from an interrupt that is different than returning from a subroutine is that you have to put those flags. Remember, the ALU flags have to be restored somehow. There might be some other status that's affiliated with any specific CPU that also would have to be restored in some way that doesn't normally have instructions that are available to you as a programmer to just simply say, hey, set all the ALU flags to this value right now. I mean, there could be an instruction to do that, but it would have no purpose other than to be used as part of returning from an interrupt handler, okay? So usually there's a special instruction that says, look, this is returning from a subroutine, but this is a special one that handles interrupts. So not only do you want to get the old program counter set back to where it was in order to go back to where it came from, you also need to set other status information in the CPU that is only affiliated with a special processing of interrupts. In most CPUs, you're going to find this sort of thing going on. There's a way to say, allow interrupts to occur from now on, or stop interrupts from being allowed, and an interrupt may have taken place, and the CPU, like you saw earlier, has a special way of figuring out where the special subroutine is to deal with an interrupt, and when it's done, it'll say return from an interrupt, go back to where we were, and reset all the statuses of the CPU so that whatever program was disrupted is none the wiser, other than perhaps that a greater amount of time has elapsed between 2 instructions than what normally would occur, okay? I mean, after all, wouldn't it, I mean, if you think about it, how would you ever write a program if, any time at all of the status flags could change for no reason? Basically, you couldn't write a program that way. So you have to save the state that could affect a sequence of instructions at any time that you allow an interrupt to take place. Here's a startup code for a freestanding RISC-V program that you might see, right? You initialize your global pointer, you might clear out the BSS and initialize any libraries that you might want to use in your program, and then you eventually would want to go off and call, the main, start the program going at the expected entry point. Now, this is a bit of a contrived example, but it's not out of the question that a freestanding program that allows hardware interrupts to take place, while it's running, maybe you've got a code, maybe this is a program that calculates pi out to, gazillion digits that runs for hours on end, and you want to read data from a UART or something like that, so a user could hit a key and stop it. Maybe that's your program, okay? Well, you could constantly check the status of your UART, asking, hey, has any data arrived? Maybe in your loop of your program. Every time you go around your loop, you check to see if there's something going on in the UART, right? Well, if you kind of think about it, the normal case is that there would never be anything ready. So checking it is a waste of time. But it would be nice to have some way of finding out that data has arrived so that you could react to it and decide whether or not, the user pressed the stop key or whatever you're going to do for commands, right? That's one purpose that you could use these interrupts for. You just write your code naively and let it spin forever. Let it get interrupted when some special thing happens, like data has arrived that need to be processed and stuff like that, okay? So what do we do? Now, this is going to vary widely depending on the manufacturer and the features in your CPU, even if it's just a RISC-V processor. They're not all going to be the same, okay? One way to do this, and this is incredibly common, by the way. This is a lot like how an ARM processor works, okay? I've dealt with those as well. What happens is there's a special register in the CPU. In the RISC-V, this is the name of one of them because there's actually a couple. But for now, let's just talk about, the basic, most rudimentary RISC-V processor you can go out and buy that has what's called a machine mode. Okay? Therefore, there's the machine interrupt vector register. And you use a CSRRW instruction like this, or you can. There's other ways to do this. But this will allow me to say, look, put the address of a subroutine into a register. Take that register and store it into the MTVEC control and status register. Okay? That tells the heart that's executing this instruction right here where to go if it ever gets a trap or an interrupt request. Okay? Now, on a RISC-V, you end up, there's different, again, it depends on your manufacturer, but in the simplest case, what happens is all traps, like illegal instructions and things like that, and all interrupts can be handled by one single subroutine. All right, see this underscore IRQ handler. Let's look ahead a little bit down here. See, I have a label down here, IRQ handler down there. I can simply say, put some code in here and do whatever I want. This is, in the code that I'm showing you right now, my interrupt handler that will get called if an interrupt or an exception ever occurs, okay? So that's where that label comes from. Let's go back up here. Now, this simply tells the CPU where to go if an interrupt occurs. These two sets of instructions down here have to do with, just like the 6502 with the CLI and the SCI, we have to say, hey, allow them to occur now. Now, unlike the 6502, in those days, integrated circuits were very large, okay? We could not fit a lot on one CPU like you can today. You can put a lot of things on CPUs, multiple cores, and you can put timers and all sorts of other things all in one physical package, all right? In the mid-70s, no way. You bought a CPU, it didn't even have a cache, for crying out loud. There was no virtual memory, nothing like that you could ever get in a single chip CPU in 1975, okay? If you wanted a timer, you bought a separate physical chip and you cobbled it all together that way. Nowadays, you can get all this on a single chip. Therefore, what we're really doing here is programming a lot of things instead of just one simple thing. if the RISC-V was so simplistic that it really was the same level of complexity as a 6502, what would happen is we would have to let it know where to go when an interrupt occurs, okay? And we'd have to know to tell it to allow interrupts to occur now. This is how you say turn on the recognition of interrupts from now on. Okay, you set the M status. You set one of the bits in the M status register that's represented by this hex 80 right here. Okay, now the part that's more complicated, because we can do more with one chip than we could back in the day, is this up here. The actual CPU for RISC-V quite often will include peripherals right inside the same physical chip. Therefore, if we have a timer, we can say, hey, I want to let that timer generate interrupts to my CPU when they're enabled. Okay. I also might want to say, external interrupts from physical devices that aren't inside the CPU socket, let those also generate interrupts for my CPU. Okay. So if you look at this hex value, you'll see 2 bits are set in there. Those are the external interrupt enable and the timer interrupt enable. So later on in my main, I might say here, set the timer to generate an interrupt after so many clock ticks. And I'll have basically a free running clock. I'd say once a second, generate an interrupt. And I could actually use that, and I could update a display, and it could count at once a second. If I wanted to build a clock, for example, into my application. Okay, so we've made, in the simplest CPUs, this basic progress over the years. In a more advanced sort of way, there could be a whole lot more than this. All right, but in a RISC-V, this is about as simple as you can get. Say, here's where I want the program counter to be set to if an interrupt ever occurs. Allow these types of interrupts to take place, and I can turn them on and off willy-nilly anytime I want by using this, by changing the value of this bit in the M status register. Okay. After that, I just start up my program, which could do anything it wants, and it would unknowingly be interrupted if, say, the timer counted to its maximum value. All right. So what do we do? On a RISC-V, the same thing would happen in a 6502, by the way, just about any CPU. Now, a RISC-V has 32 32-bit registers, and a 6502 has like 4 8-bit tiny little registers, okay? Somehow, if you're going to execute code, you need to save all the registers that you're going to use in here so that when you go back, and here's the special return instruction for a RISC-V, when you go back to whatever was interrupted, I should say, we need to make sure that all the registers are the way they were before this code up here was executed, all right? So what happens is you have to save all of the registers somewhere. In the simplest of situations, we can do it like this. Look closely at what I've done here. If you only have one heart, or you have multiple hearts and one and only one heart has interrupts enabled, okay? You have to be careful if more than one of these does this at the same time, is my point. And I need to be able to save all the registers that I might use, okay, so I can get them back. What do? I can create a bunch of save areas, one for each register that I want to save, and just store them somewhere. Store word X1, store word X2, store word X3, and so on. Remember that the %low assembler directive says to take the address that represents this label here, save X1, which is sitting over here, and use the bottom 3 hex digits, right, as this immediate value. And then add that to the contents of the register over here, which we know is always 0. In this particular case, we can be certain that as long as this label is in the first 2K of memory, we know that the top 5 hex digits will all be 0. Now, this is why you'll usually find an operating system or even a freestanding program like the one we're looking at here might treat the bottom 2K of memory as somewhat special. It's the only part of the memory that these instructions can directly address without the need of setting up a base register. Okay? And a lot of CPUs have features that are like this, all right? So quite often, the first page or half page or some amount of memory down near address 0 is treated specially, okay? In this case, we're using it to hold a save area specifically for our interrupt handler so that we can save all the registers that we want into that save area without changing the values of any registers in the process of doing so. Okay? Now, if you really think about it, all we really need is to be able to save a single register down here, because once we've saved just one, we could use, for example, X1, once we've saved it, we could use that in an LA pseudo instruction in order to set it to a new base value so that all the other registers could be saved somewhere else if we really wanted to. Okay? Now, in this example, I've kept it very simple. Just save all 32 of them right down here. Okay? There's more than enough room to do that. If your program's more complicated or you have multiple hearts running, this gets more complex because each heart will have to have a different save area. Okay? And, how do they know which one they are? If I can't modify any registers, how do I find out my heart ID and things like that, okay? It turns out that on a RISC-V, there's a special extra register called a scratch register inside of one of the CSRs that's actually specifically there for this exact purpose. So you can save any one of the registers you want and then set it up as a base register. You can use it for whatever you want and go from there, all right? I'm just saying this can get more complicated to whatever extent you need it based on your application, all right? In the simplest of terms, though, just save all the registers, do whatever you want, and when you're done, restore the values of all the registers, and then use in this case, the CPU requires a special return operation to take place so that you can get the program counter reloaded from the place where it's saved. It turns out that the RISC-V, when an interrupt occurs, does not save a program counter in a stack. All right? That's only for super trivial little CPUs like the 6502. All more advanced ones have a special place to save the program counter because if you think about it, what if the stack pointer is invalid? And what if it's pointing at an illegal address and that's why you got an interruption in the first place, or in that case, an exception, okay? Then you'd get an exception while handling your exception, which is a real problem. That if you're on a 68K, there's actually a special status for that. It's the interrupted exception handler, and the CPU seizes up when that happens. It goes into a special state where it's an interrupted interrupt, and of course, then your computer is seized until you reset the thing, all right? So you got to be careful that doesn't happen. Now, the way the RISC-V deals with it is, like I said, there's a CSR called the MEPC, for the Machine Exception Program Counter Register, that's there specifically for the CPU to store it in there so that the memory system doesn't even need to function in order to handle an exception, okay? And this special return instruction is there that says set the program counter equal to the value in the MEPC register so that it can go back to wherever it was when the interruption took place. Now, like a lot of other CPUs, once the doc is spelled correctly, it has to potentially restore other things, all right? Now, in this case, just like the 6502, the RISC-V, for the same reason, will have disabled the interrupt requests, okay? So along with getting the program counter back to where it's got to go, this will restore whatever the interrupt request mask was before this handler was invoked in the first place, okay? Most specifically, the bit inside here would have been shut off, okay? And to set it back to the way it was, automatically, as part of returning from this interrupt handler, you use the mReturn instruction. So let's look at a practical example then of how we use all this. Let's say we have a system. We want to write a freestanding application, all right? We don't have an operating system. We're going to basically write a super simple one that has 2 threads of execution running with a preemptive round-robin scheduled multitasking kind of scheduler, all right? So let's say we have 1 heart in our system, or 1 core, okay? How do you do that? Well, what you do is you have the code for each one of the threads that you want to have running. And in this example, they both have an endless loop in here. Neither one of these will ever return. Okay, it simplifies our lives a lot if that's the case. And remember, in a freestanding app, it just runs when the power's on. So if it ever returns, what does that really mean? I suppose if the machine could shut itself off, it could do so when it's done. But in this simple example, let's just assume that there's some sort of an infinite loop in each one of these 2 threads, okay? Whatever they're doing, they're gonna just do. Maybe this one's calculating pi, and this one's adding up all the prime numbers or something like that, all right? Point is, neither of those has an end. They run forever. So what do you then do? We're gonna create a save area for each one of the 2 threads, and they're going to be the exact same thing. You could define like a struct or something like that if you wrote this in C. The idea is you remember the current thread that's going to be executing. This is a simple pointer variable that points to one of these 2 save areas. Each of these save areas has enough memory in it to represent a storage place for the 31 modifiable registers on a RISC-V CPU, right? And a copy of the program counter that's needed that represents the address where the thread will resume if it starts running or resumes running in its next opportunity. So what we have here, maybe we'd set all the saved register values to 0 before this thread starts running up here, and we would set all these to 0 for the thread down here. The point being that the program counter for thread 1 equals the address of the function that's supposed to start running when thread 1 runs the next time it has an opportunity to do so, and the save area for thread 2, the program counter saved value would be set to the address of where the thread 2 function is supposed to be. So to make all this work, in your startup code, you're going to do these things here. You're going to initialize these save areas. You're going to initialize the hardware counter and timer circuitry, however that might work for the CPU and hardware that you're working on. You're going to enable interrupt requests so that when the counter and the timer generates an interrupt next time, your handler will be invoked, okay? And then you're going to start the current thread. And this operation is simply defined as go up to this current thread variable up here, grab the address in there, and set all the registers to the current saved values, and go to the address in the PC register. Now, in order to actually do this, you're going to have to be a little bit crafty, because if you load all the registers with their saved values, you don't have a base register around to use to get this address of the current thread, instruction to execute into the program counter. So again, this all depends on the kind of CPU you're using. If you have a RISC-V, you can use the scratch registers or the MEPC register to make this happen. All right. Now, before we go, let's look at what you might do in a freestanding program. This is kind of a pseudocode-ish assembler here, all right? Most of this will compile, but it'll depend on the kind of machine. You'd have to tweak this a little bit, all right? So this is not going to just work on anything, but it's similar to what you might expect to find, all right? The usual initialization code you'd do up here, and to set up our round-robin scheduler, we're going to keep track of our current thread, okay? We're going to essentially say, look, set the current thread variable to point to the thread 1's save area. That's what's going to happen in here, right? Then we're going to configure and start up our timer, and we're going to enable interrupts as appropriate for the variant of your processor. And then you're going to say, begin one of the threads. Now, notice that this code here doesn't have specialized code that will actually be used to start a thread running the first time. We're always going to look at this in terms of resuming it after it has been interrupted. So let's kind of look at, let's come back to how this starts the first time. After we look at what's happening, let's assume it has started, and look at what happens when it's interrupted and how it resumes after it's been interrupted. Then we'll contemplate why we can do this, all right? So what happens in here? Here's my interrupt handler. And what am I going to do here? I'm going to come in here. I'm going to store X1 in the scratch register for the heart that's been interrupted. Then I'm going to use X1 to point to this current thread's save area. Now, this code doesn't care whether thread 1 was interrupted or thread 2. It doesn't matter. What it's going to do, it's going to save the current thread's context in whatever the current thread's save area is, because, as we'll see, this thing is always set to point to the save area for the current thread that's executing right now, okay? So what is we going to do? We're going to say store X2 through X31 at all the respective locations in these save areas, right? Let's take a look down here at what these things look like, right? We got enough room to store 31 registers. Why store register 0 when it's always 0, okay? So we're going to store X1 through X31 in here, and we're going to remember where the program counter was when this thread was last interrupted. In other words, this is the address to go to resume that thread running the next time we want to start it up. And as we see here, as written, the initial values here, these would be the names of the threads, the functions that represent each of the two threads. So somewhere in my C program that this would get linked with would be a void, maybe thread1 underscore entry open and close parentheses. You know, that would be the name of the function that's supposed to run for thread 1, okay? Likewise for thread 2, the current thread variable down here is going to be set to point to either this or that save area. And as we saw a minute ago, we initialize it to point to thread 1 save, okay? So if thread 1 is the thing that is running that got interrupted here, then what happened would be that X1 would be set here to point to thread 1 save. We would be saving all 30, well, we would save 30 of the 32 registers here, right? 2 through 31. Then, because we saved X1 in the special scratch register, because we needed to set up and use it as a base register for the rest of these saves, okay? Then we say, take that scratch value that we set to X1 up here, copy it into some temporary register like X2, and then store that to where X1 should have gone in the first place. Okay? At this point in time, we have saved all 31 registers that we care about for the thread of execution that has been interrupted in the save area for whatever the current thread that was running is. Okay? Now, when we're totally done, we need to save the program counter as well. Okay, so that we can come back to it later. And the RISC-V has a special register for that. When it was interrupted, the program counter is saved in the MEPC CSR. So we're going to copy that into a temporary register, and then we're going to store that into the save area as well. And 7C off of X1, if you do the math, is where the save area is for this word down here relative to the beginning there, as well as this one here from that save area. Okay? So at that point in time, we have saved all the registers and the program counter. So we've saved the entire state of a running thread. So now we can do anything we want, and we have everything we need to resume and start that thread again later if we want to. Okay? So now let's look and see how we switch over to running the other thread. Okay? So in this example, this is a very naive example. We're going to just assume that any interrupt for any reason that occurs is from our counter timer type circuitry. And all we're going to do is change to over to the other thread of execution. Okay, so here is what we would do after we've saved one thread. We would come down here and we'd say, look, which thread was running? Okay, this is just a simple brute force if then else. So we're going to say, take the address of the thread 1 save area and put it into x2. And we know that x1 is still pointing to the save area for the whatever thread was interrupted. Okay, we're going to compare these two. If x1 is pointing at the thread 1 save area, then we want to resume the execution of thread 2. If it's not pointing at the thread 1 save area, then it must be pointing at thread 2, and we want to instead to resume the execution of thread 1. And now you see the label that we jumped to above, by the way. We'll come back to that in a minute. We've saved whatever thread was running, and now we've decided whether we want to resume the execution of thread 1 or the execution of thread 2 with this simple if-then-else up here, okay? So if we want to resume thread 2, we jump down here and we set x1 equal to the save area for thread 2. If we want to instead resume thread 1, we set x1 to point to the save area for thread 1, and we branch over down to here, okay? Again, simple if-then-else type of thing. So what do we do down here? We're going to do the opposite thing that we just did above when we were saving the state. This time we want to restore the state or resume the execution of a thread. So how is that going to work? Well, the first thing we need to do is kind of think ahead here. Ultimately, we're going to use the mReturn instruction. So again, we're thinking ahead here. What are we doing here? So we're going to put the program counter value that we ultimately want to return to after the interrupt handler is done into the MEPC register. After that, we need to restore the 31 registers. Okay, now we've set the X1 as a base register already, so we can just simply reload X2, X3, X4, X5, and so on. Now make sure, of course, you do X1 last, right? Because once you've altered X1, you've just destroyed your base register, okay? So the only really critical thing of the 31 registers is that you use your base register. You need to load that one last. And after that, you simply say mReturn to go to the program counter that was stored in the MBBC right there. Now, let's look down here again. Before this program even runs, the initial values that are stored in these save areas are as written. It turns out these will all be set to 0 because that's what the space directive does, right? And the word directive says, give me a 32-bit value and initialize it to the value of this symbol, the address of these would-be functions, right? So when this program starts running the very first time, what happens is we put the value of thread 1 save, the address of this save area, into the current thread variable. And then down here, we go to resume thread 1, okay? And resume thread 1 sets the base register for X1 to thread 1 save. Comes down here and loads all the registers from the thread 1 save area. And because we initialize it with the address of the function that represents the entry point to the code for this thread, it'll start executing at the beginning of where it's supposed to be. Obviously, if it's ever interrupted, this code up here will modify that every time there's an interrupt. When it saves its state, the value at 7C off of the save area will end up getting updated with the value of the new program counter return address, okay? So what's going to happen is every time there's a timer interrupt, it will toggle from executing the code for thread 1 over to the code for thread 2. The next time there's an interrupt, it'll save thread 2 state and toggle back to running thread 1. This is exactly what a round-robin scheduler is going to do. So if you have the simplest possible case, no operating system, but you've got 2 threads of execution that you want to do, this is a pretty simple way to make that happen. So I hope this gives you some insights as what interrupts are, what exceptions are, how they're handled, and a simple scenario on how you'd use them for a simple 2-thread round-robin schedule. Thanks for watching. See you next time.